Welcome, and my name is Shahar Belkin. I'm the Executive Vice President of Product in ZutaCore. Actually, what I do is translate the information between the market and the R&D, and from the R&D to the market, because they talk different languages. But I want to tell you about the ZutaCore system that is called Hypercool, and it is direct-on-chip cooling, but waterless, without any water in the servers. And I want to start very quickly why it's needed, although I'm not talking about ZutaCore, I'm talking about the direct-on-chip liquid cooling, is that the industry is running out of air, meaning that power of the chips is going up rapidly, and at the same time, maybe not as understood yet, the case temperatures of the chips are going down, meaning that air cooling will not cope with the ability to cool these chips, or you'll have to use a lot of more energy to cool them. And at the same time, what's happening in the industry is that there's being pushed to reduce energy and reduce carbon emission, and those two collide and create an environment the data center could not solve without moving into direct-on-chip liquid cooling. And that's where ZutaCore is coming with some additional competitors. And if we look at ASHRAE, I don't know, probably some of you know what ASHRAE is. ASHRAE last year released a white paper saying that direct-on-chip liquid cooling is moving into the mainstream of data centers and not only to the high-power computing. And what you see in that graph that they released is that above 300 watts, it is almost impossible to cool by air, and you will have to move to liquid cooling. And if everybody knows here or not, next year, in the beginning of next year, Q1, AMD and Intel both are releasing their new generation CPUs with 350 watt power consumption of these CPUs. So looking at ZutaCore being the youngest player in the industry of cooling, we have looked at the industry, what's already out there for solving that problem that we understand and know that needs to be solved almost immediately. And we saw two different kind of solutions. One of them would be immersion cooling, and that has big tubs that you put the servers inside, and one of them would be cold plates, like CoolIT or any cold plate that is using water. Those are the solutions that are out there in the market, and that's the majority, or almost 100% of the market is based on those. But when we looked and asked customers, one thing we were told, guys, we don't want water in our servers. We don't trust technicians all year long to use those servers and not have a leak ever. So one thing was clear to us that we need to find a solution that not includes water. And then when talking with them about immersion, we heard the same thing of they have to change the whole data center from racks, from the way they do it today, to tubs with liquid, with oil, with cranes, with dripping, and all the rest. So when we looked closer, we decided that water will not be the way we're going to select, because we need a way to have very, very high scalability to go to not 1 or 2 racks, but 1,000 racks. So putting water in 1,000 racks is putting in a lot of maintenance that needs to be done on the water, not on the servers. Water needs to be chemically tested all the time. Water needs to be replaced. There's biological growth. There's changes in the material. And this is a headache that we decided to prevent. When we looked at immersion cooling, it was a very good solution for cooling, but it has caveats. And each one of the solutions out there in the market has its own limitation or hurdles. And we decided to come out to the market with a solution that generally has no hurdles to come into the market, has no limitation, not specific server, and not specific rack. It can fit anything. And this is what you see now. The solution that we came out was keeping the racks as they are, keeping the servers as they are, not providing any harm or any danger to the servers, because we're using a dielectric liquid instead of water, and a very, very simple, and if it's not simple, it won't work. It is simple nylon tubes inside the server, retrofitting or coming out of the factory. That's what you see in the picture here. And the most important part, it does not introduce any danger to the servers whatsoever. There's no compatibility issues, and there's no short by water issues. When we looked at the data center solution, we looked at how do you put a solution like this without having to change your data center, without having to change the way you do maintenance. So the solution we brought is keeping the same infrastructure you have today, the same racks, the same servers, the same way you did it until now, the same way you maintain the servers, you can pull it out, the same components in the server. You don't need to change the component. You don't have to be limited to only specific hard disk or specific memory, specific network cards, because the liquid is not touching and not affecting anything in your server. And last, we looked at a solution that will be future-proofed, meaning it's not that this is a good solution that when chips will go from 300 to 500 or 500 to 700, then your solution will have to be replaced again. No, this is a solution that can go to 1,000 watts and beyond per chip. And this was very important to find a solution that not only solves the cooling, it also provides a very efficient way to reuse the heat. And that's what we developed. And I want to talk about what our solution actually is, and this is where I'm starting. The cold plate is just like any other cold plate. The cold plate fits exactly like the manufacturer has put the heat sink, replacing it with the same screws, with the same kind of attachment. But because there's no liquid, we don't care if one at a time, one of a million, you'll have a drip. It won't make any danger. The liquid is completely IT friendly and IT safe. There is zero material compatibility on the server. None of the components, none of the memories, none of the network has to be fitting or fit the liquid. The liquid doesn't touch anything in the server except for inside the cold plate. And the system is low pressure, meaning you can use standard nylon tubes. You don't need to use metallic tubes. You don't need to use very expensive connectors. It's very, very simple. It's very quick. And that's what led us to this solution. Now, not everything was as easy as I'm saying it now, meaning putting water into a cold plate, getting the water hot and taking them out is very easy. That's why a lot of companies are doing that. Doing that with the electric liquid is very complicated in the technical side of how we had to develop it, because this liquid that is the electric doesn't conduct electricity, but it also does not conduct heat, meaning you cannot put cold liquid on one side and get it hot on the other side. You need to do phase change. And when you do phase change, it means you need to have a very even phase change over the die, because this is not cooking pasta. Here, when a bubble is above 1,000 or 10,000 transistors and that bubble creates a hot spot right above them, you're not getting cooled at that specific. You have to have a technology that has a very even layer of bubbles, very small bubbles. And that's what you can see on the left bottom corner is a patent of fins and wick that we developed that actually creates a very even layer of bubbles. And if somebody would want to go into why that's happening, I'll be happy to talk after this. But the bubbles are released when they're very, very small and very even and immediately boil when heat comes in. It's not, there's no time like in pasta that the liquid has to heat up before it starts boiling. So that's one part of the development and the patents. The other part is how do you distribute liquid to hundreds of E&Es, hundreds of cold plates, without having to reduce the flow on one of them, and you have high ones 2 meters high in a rack and ones right on the bottom. Everyone has a different pressure. So what you see in the bottom left right corner is a float. The yellow part is a float that floats above a pool of liquid. And when the chip is idle, that float goes up and closes the orifice of liquid that no more liquid would come in, so there's no circulation of liquid. And when boiling starts, vapor comes out, the level goes down, and more liquid comes in. So it's fully automatic, fully on demand, and there's no actually control, no electronics, and no software needed to control that. And the one positive or the extra thing we got is out the tube of the vapor, there's 100% vapor coming out, making the condensing very, very efficient and very well done in this scenario. So how does the system look like? What you see on the right side, condenser at the bottom of the rack, and you can see a demo there in the lobby. Servers are all over the rack. You have a manifold, a very simple aluminum manifold on the side of the rack, just about the same size as the PDU, the power distribution unit. And every server is connected by 2 tubes into this manifold. What you can also see is all the components, all the servers, everything in the ZutaCore system are in parallel, meaning none of the chips, and you'll see that in a moment in the presentation, that we'll see the benchmarking, none of the chip is affected by the other chip. I mean, one can be idle, one can be full, both of them can be full. There's no effect between one to the other. Everything is in parallel. Everything is exactly at the same temperature, all over the rack, and that's important. What you see on the left side, this is actually the closed loop of the system. Vapor that comes out from the evaporators, from the ENEs, go into the condenser, collected all in the condenser. The condenser is condensing them, but the condenser actually has a speed control in the condensing, meaning it controls the pressure. And by controlling the pressure, we can actually, you can, as customers, can actually control what would be the temperature of the CPU. It's not a cooling system that cools as much as possible. You want the chips to be 60 degrees or 70 degrees or 80 degrees or 50. This is a parameter that you can control, and the system will keep the boiling temperature at the temperature that you select. And then the liquid is being put into a buffer and pumped back into the system, giving a closed loop. This pump is also controlled by the pressure, because what we saw before in the evaporator, pressure of liquid always has to be higher than pressure of vapor in order to go into the evaporators, to the ENEs. Now, ZutaCore has been working with the silicon manufacturers, and today when you design a server, if you're a server manufacturer, you can find in a thermal design guide from AMD or from Intel. This is, for example, this is Intel, the Sapphire Rapid, the new generation coming out next year. You already have in the thermal design guide their guidance that if you want to use two-phase, ZutaCore is their solution. And this was a hard place to get to. It looks like a line on a paper, but it was hard. It was about 1.5 years of testing in Intel labs until they got this into it, and working with AMD very closely on their chips into releases. What do you get from ZutaCore? You got a few components. The evaporators, the ENE, different ENE for every component because they have different sockets. They have different screw designs. And you can see here some examples of these evaporators for CPUs. You can see the Milan from AMD. You can see the Sapphire Rapid from Intel. And the Genoa coming out also from AMD. And we also have different versions for flat and for blades because of the direction the vapor is coming out. That's the reason that it is here. And the other component, the other part, is the condensing side. Condensing side, we have 2 families of condensers. One of them work with air. Work with air meaning it takes cold air from the input, from the cold aisle, and it puts the hot air back into the hot aisle if you have it, but to the back of the rack. And these air solutions are very, very unique because you don't need any infrastructure in your server room, in your data center. There's no changes. You put it in the bottom of the rack, you install the manifold, you install the units, you install in the servers, and it's working. There's no infrastructure changes. There's no need for any water brought to the rack. And you can get with air up to racks of 50 and 60 kilowatts that you can see on the right side of the picture. This is a rear door condenser that takes the air from the servers, use that to condense the Novec and turn it back out. And this can go up to 85 kilowatt racks. In the middle, we have a family of water-based HRUs. Water-based is not that water is going to the servers. That will not happen for ZutaCore. Water is used for condensing the vapor back into liquid. And that means we use what is called a heat plate exchanger inside. Water comes in, water goes out. Cold water comes in, or warm water comes out, and hot water come out of the system. And in this case, this will be the perfect match for a reuse of heat, because in this case, the hot water can be promised by us to be higher than 60 degrees Celsius for efficiency of reusing of heat. This is a short example of how easy it is to retrofit a server. In this case, it's a Dell server, but you just take the heat sinks off and put the ZutaCore solution right above the chips. And as I said, nylon tubes, very, very easy to connect, and immediately you have a solution that is direct on chip liquid cooled to any server, any model. If it's side by side or shaded one behind another, it doesn't make a difference into the ZutaCore solution. So as I said, we have different models, but the difference is just in the tubing. You can see how simple it is to fit any kind of server, any kind of solution to a server, and that's what's important to see here. And we're working with multiple vendors of servers that in the near future you'll have a solution brought directly from them. This is just the way the rack would look after it's installed, after it's retrofitted, and again, how simple it is to take a standard rack and turn it into a ZutaCore cooled rack. And you put the HRU, you connect the HRU with 2 tubes, very simple connections into the manifold, and actually the rack is ready to be used, and the server is connected to the manifold. That's it. The last component is a software component that we call SDC, software-defined cooling. And in this component, it is not a must. That's an important part. This component gives you very, very good visibility of what's happening in your data center, in each one of your servers, and I'll be happy to do a demo in the lobby over there where it's installed. But the software has unique features of looking at your data centers, looking at the servers from the inside. It's reading the information from the CPUs and providing a very, very good granularity of looking at what's happening in each one of the servers, each one of the CPUs, and also having the ability not only to giving you a good picture and alerts if something is going wrong with any of your servers, it also has 2 unique functions that I will not go into at the moment, but to reduce the power consumption of the data center by reducing the clock speed of CPUs that are more than 30% idle time. Meaning because it's monitoring the idle time all the time, when a CPU is in idle for longer than 30% of a second, it reduces the clock speed and reduces the idle time, and by that, reduce the power consumption of that CPU. That's one possible function that is in the software. And the second one is actually taking the other side, and that is maximizing the temperature of the CPUs to their maximum level or limit, and by that maximizing the water temperature output for better and efficient reuse of heat. So those are 2 functions that this software also can provide. And I'm going back to this cooling system doesn't need the software to work. It's fully autonomous and working by itself. The software has a better visibility to what's happening there because you never know. Today, most of the software that monitor data centers are looking at the air, not looking at the servers, and that's a complete different way of looking into your data center. So, quickly back to ZutaCore. ZutaCore has 3 offices, R&D in Israel, marketing and sales and support in the US, and a 3rd office in Amsterdam now for sales and support. And ZutaCore is only from 2016. Was originally located only in Israel. Today, 50 employees and growing very, very fast, and also growing the patent portfolio. We have systems working in the industry, in the market, especially in the US, since 2019, without any technical problem, without maintenance, and that's an important part. Equinix already published that, so we have systems installed in Equinix. And we have multiple customers. Here we are led by Boston, mainly in Europe for main distribution and for support. So I'm ending here by just saying that the Hypercool solution from ZutaCore is a solution that fits the market needs and at the same time overcome all the drawbacks of liquid cooling that are existing in different solutions. Each one has its own drawback, and it's future-proof. That's it for me, and Konstantin.
So, yeah. Thank you for your time. Okay. Zurück zu Deutsch. Ich glaube, das ist beim Publikum etwas besser. Ja, wir hatten diese Lösung jetzt bei uns aufgebaut und getestet in unserem Lab in UK. Und der Test wurde gemacht von Tom Mikalski, das ist unser Senior FAE für Kühllösung, die hat nur leider jetzt gerade Covid. Von daher werde ich das jetzt präsentieren. So sieht das Ganze dann aus. Hier rechts sehen Sie die HRU und darüber dann halt die Server, die wir jetzt getestet haben. Wir haben 2 Server getestet. Und der eine Server ist ein klassischer Big Twin Server mit diesem Sled. Dabei ist zu beachten, dass wir also 8 CPUs insgesamt haben, wir aber uns jetzt nur auf ein Sled in unseren Messauswertungen fokussieren. Dieser Server ist bestückt mit einer CPU, die 225 Watt TDP hat. Und warum haben wir das gemacht? Wir wollten halt eine CPU nehmen, die wir sowohl über Air kühlen können, als auch halt mit ZutaCore kühlen können, damit wir halt danach den Vergleich sehen. Also wie warm wird die CPU, aber auch wie effizient arbeitet die CPU und hat das nachher vielleicht Einflüsse auf die Time to Solution. Neben den CPUs ist noch ein bisschen Arbeitsspeicher verbaut, aber es ist halt eine CPU-Heavy Node. Der zweite Server ist auch ein sehr populärer Server von uns. Und das ist ein Server, wo die CPUs Side-by-Side angeordnet sind. Das heißt, wir haben auch dann definitiv keine Abschirmung von der Windströmung gesehen. Das heißt, im Airflow, normalerweise, wenn wir den Big Twin haben, dann haben wir die eine CPU jetzt vorne, die kriegt die kalte Luft und die hintere CPU kriegt dann schon die vorgewärmte Luft. Bei dem Modell ist es jetzt so, selbst in der Luftkühlung kriegen beide die Luft direkt von vorne. Und das heißt, sie sollten dieselbe Temperatur haben. In dem Fall sind auch höhere CPUs mit einer höheren TDP zugelassen. Und zwar einer TDP von bis zu 280 Watt. So, das war jetzt, wir hatten vorhin jetzt die Theorie, also was ZutaCore alles Tolles kann. Jetzt hatten wir kurz die Einführung, welche Systeme wir hatten. So, was sind die ersten Resultate? Das ist jetzt für den Big Twin und das ist, wenn wir jetzt auf der linken Seite gucken, steht immer die CPU da, die bleibt gleich. Dann, ob wir mit Luft, also mit Air gekühlt haben oder ob wir mit der Two-Phase-DLC-Lösung von ZutaCore gekühlt haben. Und dahinter kommt die Ambient Temperature, das ist die Umgebungstemperatur im Data Center. Klassischerweise, desto kühler ich mein Data Center mache, desto mehr Sachen kriege ich gekühlt mit Luft. Das heißt, wenn ich mein Datacenter nach Nordnorwegen stelle und da 10 Grad Außentemperatur habe, dann ist das Sache sehr schön für meine CPUs. Und deshalb gibt es ja viele Datacenter im hohen Norden. Trotzdem wollen wir manchmal Datacenter bei uns haben oder vielleicht sogar noch etwas südlicheren Ländern. Und dann ist es sehr aufwendig, wenn ich eine niedrige Ambient Temperature haben will. Dann muss ich sehr viel Energie in eine große Klimaanlage investieren, die halt mein Datacenter konstant auf zum Beispiel 25 Grad Celsius hält oder sogar noch drunter. So, was sehen wir jetzt hier? Wir sehen einmal den Unterschied, dass wir halt ganz oben, dass die CPUs hintereinander sitzen. Und die CPU 1 sitzt hinter der CPU 2, das heißt die CPU 2, kalte Luft, während sie vorgeht, die CPU 1. Und selbst bei 25 Grad Temperatur im Datacenter sind wir nachher schon bei 86 Grad Temperatur auf der CPU. Das heißt, das ist für eine CPU schon relativ warm. Wenn wir das Ganze jetzt allerdings mit der DLC-Lösung machen, sehen wir erstmal, wir haben keinen Unterschied zwischen der CPU 1 und CPU 2. Das heißt, beide werden gleich gekühlt oder im Rahmen der Messungsgenauigkeit. Und wir haben eine Temperatur von mittlerer 50 Grad, was überhaupt kein Problem ist für moderne CPUs. Wenn wir jetzt Richtung 30 Grad gehen, dann sehen wir, dass wir auf Air halt dann bis auf knapp 90 Grad, auf 89 Grad hochgehen, was jetzt schon langsam in einen Bereich kommt, wo wir sagen, es könnte stellenweise auf dem Chip schon dann zum Throttling kommen. Das heißt, dass einzelne Segmente des Chips sagen, ich muss meinen Takt runterfahren, damit ich halt die physische Integrität des Chips gewährleisten kann. Und das vermindert natürlich nachher die Performance. ZutaCore wiederum, keine Probleme, 30 Grad, gleiche Temperatur, ist zwar etwas höher, aber alles noch im grünen Bereich. Und wenn wir jetzt Richtung 35 Grad gehen, da sehen wir, wir haben definitiv ein Throttling bei CPU 1 bei 95 Grad und die CPU 2, oder wir vermuten definitiv ein Throttling. Gleich werden Sie sehen, wir haben auch eins. Aber bei der CPU 1 auch eine hohe Temperatur schon und ZutaCore wieder eine gute Lösung. Das ist jetzt nochmal ein Vergleich zur 280 Watt CPU. Das heißt, wir haben jetzt natürlich 225 Watt, ist aus guten Gründen nur in den Big Twin standardmäßig freigegeben, weil wenn wir da eine zu große TDP reinpacken, hätten wir eigentlich immer thermische Probleme. Jetzt bei 280 Watt haben wir schon bei 25 Grad kommen wir schon in den mittleren 80er Bereich rein. Wir sehen in dem Fall, dass die beiden CPUs parallel angeordnet sind. Wir würden also erwarten, dass es keine wirkliche Beschränkung gibt, dass beide gleich stark gekühlt werden. ZutaCore ist beinahe langweilig, klappt wieder alles wunderbar. Gute Temperatur, gleichbleibende Temperaturen zwischen beiden. Wenn wir jetzt auf die 30 Grad gehen, sehen wir auf einmal, dass die CPU 1 doch sehr viel heißer wird. Und was ist das? Naja, ich weiß nicht, wie Ihr Hintergrund ist Richtung so Strömungsdynamik, aber im Allgemeinen ist es so, ich versuche ja dann immer die Lüfter höher drehen zu lassen, um mehr Luft durchzupressen. Und irgendwann werden Strömungen nicht mehr laminar, sondern werden turbulent. Das heißt, ich komme an physikalische Limits. Ich kann nicht einfach die Lüfterdrehzahl erhöhen, sondern ich habe irgendwann einfach keine Möglichkeit mehr und ja, ich kann nicht mehr kühlen. Und deshalb ist bei 35 Grad, sehen wir, dass dann zum Beispiel Air Cooling, die CPU 1 bleibt auch bei den 94, also sie throttelt. Wir haben eine kaputte Luftströmung im Gehäuse und wir haben ein System, was zwei sehr hochpreisige CPUs hat, die auch sehr leistungsfähig sein sollten, aber wahrscheinlich nicht zu ihrer Topform auflaufen können. Und das ist ja unsere aktuelle Generation. Next-Gen-CPUs, wissen wir, die meisten gehen definitiv über 300 Watt, die Top-SKUs, gehen an die 400 Watt ran. Das heißt, da werden die Probleme größer, weil die Physik über Strömungsdynamik, die ändert sich nicht. Jetzt haben wir noch mal ein paar Tests gemacht, wo wir eine Render-Szene gemacht haben, Barbershop in Blender, und dabei uns jetzt die Clocks angeguckt haben, der einzelnen CPUs. Das heißt, im CPU 1, CPU 2, CPU 2 sitzt, wie gesagt, im Big Twin vorne. Das heißt, die nächsten 3 Slides beziehen sich alle auf den Big Twin. Wir haben die 225 Watt CPU und die grüne Linie ist ZutaCore und die rote Linie ist airgekühlt. Ganz klassisch, wie ist es, eine Applikation wird gestartet, die Clocks gehen hoch, unsere CPU arbeitet und wenn die Applikation fertig ist, sinken die Clocks wieder, die CPU idelt, um Strom zu sparen. Das heißt, diese ZutaCore-Linien sind, wie man sie schön erwarten würde. Wir gehen hoch, wir haben gleichbleibend hohe Clocks, und dann gehen wir runter, wir idlen, wir sind fertig. Bei R ist es jetzt in dem Fall so, sieht man sehr schön an CPU 1, selbst bei 25 Grad und keiner Top-SKU, sondern einer hohen SKU mit 25, aber definitiv keiner Top-SKU, haben wir schon Probleme. Die Clocks brechen uns irgendwann ein. Und das ist das sieht man daran dann auch, dass wir halt zu viele Webinare gehabt in letzter Zeit, da gibt es so einen Mauszeiger. Dass wir halt die rote Linie geht runter und das Ganze führt natürlich nachher dazu, dass wir erst später Richtung Idle gehen. Das heißt, dass wir auch, unsere Applikation terminiert später, wir brauchen länger, bis wir halt fertig sind mit unserer Render-Szene. CPU 2 ist etwas besser, aber auch sie braucht länger. Wenn wir jetzt Richtung 30 Grad gehen, dann wird das Ganze nicht besser. CPU 2 sieht immer noch relativ gut aus, auch wenn sie natürlich auch etwas länger braucht, weil wir ein Dual-Socket-System haben. CPU 1 wiederum sieht schon sehr schlimm aus. Und das ist jetzt 35 Grad. Und in dem Moment überlegen Sie sich, Sie haben für Ihr System mehrere 10.000 Euro ausgegeben wahrscheinlich und haben ein System, was keine Leistung erbringt oder eine sehr schlechte Leistung. Ihre Clocks gehen hoch und runter und je nachdem, wie die Applikation natürlich auch geartet ist das Verhalten sogar noch schlimmer, als es hier aussieht, wenn Sie zum Beispiel irgendwie halt Multi-CPU-Berechnungen haben, die dann an einzelnen Barriers hängen. Das ist jetzt die Time to Solution und wir sehen, bei 35 Grad sind wir um bis zu 17% schneller, einfach nur, weil wir die Kühlung austauschen. Das heißt, die Kühllösung, gute Tubes, einfach nachrüstbar, sie sind 17% schneller. Und jetzt können wir eine einfache ökonomische Rechnung aufmachen. Wie kriegen wir am meisten Flops Compute Power pro Dollar hin? Oder Euro, wir zahlen ja Euro. Nochmal das Fazit, um auch von beiden Talks etwas zusammenzufassen. Also bessere CPU-Performance bei weniger Strombedarf, weil auch die Lüfter etwas niedriger drehen. Und natürlich nachher auch dann, weil wir die Hardwarekosten zwar erhöht werden, aber nicht in dem Ausmaß erhöht werden, auch eine bessere Performance pro Dollar. Die kleinen Schläuche, die es ermöglichen, dass wir das Ganze gut nachrüsten können und auch in viele Servertypen verbauen können. Und natürlich die dielektrische Flüssigkeit, die kein Risiko für unsere Hardware darstellt. Und ja, das war's mit meinem Talk.